Hello and welcome to Python Deep Learning for Beginners. We're beginning a new section today about convolutional neural networks. In this section, we're going to take a look at three things to understand convolutional neural networks. Number one, we're going to talk about how we can understand convolutional neural networks from an intuition point of view. Number two, we're going to look at implementing a CNN using Keras. And then number three, we're going to look into what happens when we create deep CNNs. We have more than one convolutional layer. In this video, we're going to talk about understanding CNNs. We're going to answer three questions to bring you through CNN as a technology. The first question we're going to answer is, what are CNNs? And then we're going to talk about going from feed-forward networks to CNNs. And then we're going to talk about what are CNNs used for. So let's go from something that we know quite well, and we try to generalize this into convolutional neural networks. In the last few videos, we talked about feed-forward neural networks, where we have an input layer with however many neurons we need to represent an input. We feed those neurons' activations through into the hidden layer, connecting every single activation to every single hidden neuron. Each hidden neuron produces its own set of activations. For example, in this current diagram here, there are 4 hidden neurons resulting in 4 hidden activations. These 4 activations all go into the 2 output nodes, as you can see from the arrows. And each output node takes all 4 hidden activations to compute the final output. So the key characteristic here is all the information from the last layer is received by every single hidden neuron in the next layer. Obviously, this has its advantages and disadvantages. The advantages being all the information from the last layer is propagated to the next layer, and the next layer has a chance to process that information. The downside of this, we're focusing on the entire inputs every time. So the neural network has no chance to learn repeating patterns, rotations of patterns, translations of patterns, and so on and so forth. Convolutional neural networks solve this problem. What we're doing is we are creating sort of like a window that slides through the input and takes the input into what we call a feature map. So very concretely, if we look at the left-hand side of the diagram on the PowerPoint, what we're seeing here is in the input robot image, the convolution itself is only applying, or I guess looking at, a small part of the robot image. In this case, it's looking at the arm and the hand component of the robot. And what this does is, within the smaller circle that's called a convolution, within the smaller square, the convolution has a set of weights for this square and this square only. And all of the information, or all the pixels in this square, gets multiplied or dot producted with the convolution weights, producing one activation from this squared area. After this one activation is produced, this square area is moved to the right for 1 pixel, or however many that you're defining, and the process starts again. So we contrast this to a feed-forward network. A feed-forward network would take the whole input, i.e. the entire robot image, and multiply as many weights as inputs on the image to produce one activation, right? However, in convolutional neural networks, we only look at a small part of the inputs at a time, and that's called the kernel. And within this kernel, we have one single set of weights for this kernel when we're producing one feature map. So if you can see in the second layer, instead of seeing neurons, we have feature maps instead. So one feature map is the output of one set of weights on the kernel, and the kernel basically gets slided through or convolved through the input image. So what you can imagine is we're now looking at a smaller subset of the inputs at a time and having a shared set of weights to compute an activation from that subset of inputs. What that means is, because we have multiple feature maps every time we create a CNN layer, each feature map allows us to capture a small pattern that is within the kernel size. One example is one feature map might capture the curve of the robot's hand, and the other one might capture a straight line that is the robot's head. And that's possible because we're only focusing on a subset or a small square within the input data and computing the activations using the same set of weights. Because that set of weights is shared across all of the kernel computations in the same feature map, the set of weights is effectively acts as like a feature detector because it will activate a particular set of contours. After the first set of feature maps has been created, we can subsample the feature maps to reduce the size of the feature maps into the third layer shown in this diagram. We can create another convolutional layer that again uses a kernel to compute higher level representations from the feature maps, and that itself creates another feature map. So in the last layer that says f.maps, like the third layer from the left that says f.maps, what this is doing is it has already created one kernel-based activation. It has subsampled those activations, and it created another set of convoluted activations on the feature maps. And then these activations are then subsampled into a fully connected layer. All of the samples are now connected to a set of neurons. Usually that's 1,000 or 2,000 neurons at the very end. So on the rightmost, you can see the purple line representing the fully connected layer, which is basically just another way of saying the normal feed-forward dense layer we're seeing. And then we're then putting this fully connected layer into the output layer. We've talked about what are CNNs. We talked about going from feed-forward networks to CNNs. And we've shown that CNNs can be used to interpret and create neural networks on top of image data like the robot image we've seen before.